We're going to look at rational functions, and I have open here the handout I gave you, which summarizes the most common function, basic versions of the most common functions, such as the linear function. This is actually the identity function, y equals x, the squaring function, x squared, the cubing function, the square root function, the cube root function, the absolute value function, very common ones we've looked at in previous sections. And now we'll be looking at rational functions, which is also part of this handout in the next page. We have rational functions, rational meaning it's a ratio or fraction, which has variables in the denominator. So you can see we have 1 over x and 1 over x squared as the most common ones we'll be looking at as far as the basic version. And the same transformations that we learned about for the other parent functions, such as shifting left and right, moving up and down, reflecting across either axis, rotating about the origin, all those things, stretching vertically, horizontally, compression, all those things can be done with these as well. But we're going to first start talking about a new concept called an asymptote. So I'm focusing on these two top boxes here. This one, which you can see has the behavior that the function, as you get closer to the y-axis, coming from this direction, from positive infinity for x values, if you're moving backwards towards the y-axis, the function doesn't want to touch the y-axis, and it veers off and starts heading towards positive infinity, and it just keeps getting closer and closer and closer to the y-axis without ever touching. And the same thing happens here, coming from negative infinity. There's also a horizontal asymptote with the same type of behavior, where the function never wants to cross the x-axis. So let's think about why this makes sense for this function equation. First of all, the domain probably makes the most intuitive sense. We know we can't divide by 0. We'll get an undefined result. In other words, the graph of the function can't exist for x value equals 0. So x equals 0 is actually the equation of the vertical line, which is the y-axis. So every single point along the y-axis has an x value of 0. So that makes sense why the function does not want to touch or cross that line. And that's what we call a vertical asymptote. Now the y also can't be 0, and that's the equation of the x-axis. The x-axis has the equation y equals 0, horizontal line. And that's because in the numerator we have a constant, and no matter what you divide a constant by, you'll always have some substance, no matter how large the value is that you're dividing with. If you get really large values in the denominator, your quantity will become very tiny and approach 0, approach nothingness, but it can't actually ever be completely nothing. So it makes sense also for that reason why we see a horizontal asymptote where the function doesn't want to cross or touch. For 1 over x squared, the behavior is different because the x, when squared, any value you plug in for x, when you square it, will be a positive result. Because if you do a negative times a negative, you get a positive. If you do a positive times a positive, you get a positive. The only exception is if you actually plug in 0, and 0 squared is 0. And so again, you would have an undefined result at x equals 0. So once again, we see a vertical asymptote through the y-axis, which has the equation x equals 0. And coming from both directions, instead of having one side that veers off towards, like right here, let's go back to this for a moment. On this side of the y-axis, if you approach the y-axis, the function veers off towards positive infinity, and on the other side, it veers off towards negative infinity. But that doesn't happen here because, again, everything's going to be positive. We have a positive in the numerator. We're definitely going to have a positive denominator. So a positive divided by a positive will always be positive. So we see the same behavior on each side, that we're veering off towards positive infinity as we approach the y-axis. Also, once again, the function itself can never be 0 for the same reason that the function here could never be 0. So we have a horizontal asymptote also at y equals 0. So the domain for this side, for the reciprocal function, the domain would be all real numbers except for 0, and the range would be all real numbers except for 0. The function 1 over x squared will have the domain of all real numbers except for 0, and the range is actually going to be greater than 0, strictly greater than 0. So no negative y's, y can't be 0, but it can be above 0. So from 0 to infinity for the y values. So there you see the reciprocal function in the textbook with the domain and range stated in interval notation, and the facts that we've just been discussing here. So you can read up on that some more if you would like to get more detail. And then we have another example which has a negative coefficient, which means it's flipped across the y-axis. So now you see opposite of the parent function, which had this part in the first quadrant and this part in the third quadrant. When you put a negative in front, it flips across the y-axis. So it flipped upside down. Also, it's a little bit steeper. Notice that it's a little bit farther. There's more space in this region here underneath that curvy part, and also in here. And that's because the numerator is larger. So there's a vertical stretch on this. And let's look back at the original parent function again. Yeah, you can see it's a little bit closer to the corners there than this one is. You can see it's kind of raised up a little bit. All right, this example, we have 2 over x plus 1. So this time it's not going to be flipped upside down, but we do have a horizontal shift to the left 1 unit because x has an addition of 1 on it. And remember that whatever sign is being applied to the x value, you're moving in the opposite direction. So that would be a shift to the left. So let's look at the graph. So you can see this looks like the original parent function. It is stretched up by a factor of 2 again, and it is shifted to the left. And so the asymptote, which used to be at the y-axis, has now shifted over to x equals -1. All right, and here's the rational function 1 over x squared, which looks like a volcano. It's the basic parent function. And then we have the example 3. This looks like it's going to be shifted to the left by 2. And down, remember when you're adding a value onto the outside of the function, that's a shift on the y value. So this is actually going to go down. It moves the same direction as the sign by 1 unit. So we're going to see that the horizontal asymptote will drop down, the vertical asymptote will shift to the left 2 units. So let's look at the graph. So there you see the asymptote shifted over to 2, and the horizontal asymptote dropped down to -1. Okay, so after just kind of looking at what makes sense to us, let's read what it says formally here about asymptotes. It says, let P of x and Q of x define polynomials. Consider the rational function which has a polynomial in the top and a polynomial in the bottom, written in lowest terms, which means that you would assume that any factors that can be canceled have been canceled. Then if the absolute value of y is approaching infinity as x is approaching a certain constant, written in lowest terms in real numbers a and b, then the x equals a, which is a real number, so that represents some vertical asymptote, such as in this example, a would be -2. The vertical asymptote is at -2, so that could represent a here, or a could represent that. That would be a vertical asymptote. And so it says as the absolute value of y gets larger, then the line x equals a is a vertical asymptote. And if f of x, y approaches a constant b as x approaches infinity, or rather as the absolute value of x approaches infinity, then y equals b is a horizontal asymptote. Okay, so looking at number 1, if the absolute value of y is approaching infinity as x approaches a constant, meaning, so what that means is, here's the constant x equals -2. As x is approaching that vertical line, the y value is veering off towards positive infinity, and likewise over here. So therefore, the vertical asymptote is -2. And likewise, if the y value is approaching a constant as the absolute value of x approaches infinity, then we have a horizontal asymptote. So once again, as x is approaching positive infinity, y is approaching a constant -1. And also as x is approaching negative infinity, y is approaching a constant -1. And that being that x is approaching negative infinity, the absolute value is approaching positive infinity. So that fits this statement here. And also looking back at the reciprocal function, seeing that, I went too far, go back a little bit. Seeing that number 1 said if y, or rather the absolute value of f of x, is approaching infinity. So the absolute value of y here, y is approaching positive infinity, so the absolute value of y is approaching positive infinity. Here y is approaching negative infinity, or in other words, the absolute value of y is approaching positive infinity. And as that's happening, x is also approaching the constant x equals 0. So x equals 0 is the vertical asymptote. All right, now we've talked about vertical asymptotes. To find a vertical asymptote, you just need to set the denominator equal to 0 and solve for x to know which value you don't want to include in the domain. And that'll be your vertical asymptote, which I think of as sort of an electric fence that creates a barrier for the function so that the function has to veer off. Then we have other asymptotes. The horizontal asymptote is a little bit more interesting how we figure that out. And that's outlined right here, very wordy way, and I'm going to simplify it down. But this is as I'm discussing this, it's coming from these formal definitions or axioms. So A says if the numerator has a lesser degree than the denominator, then there's a horizontal asymptote at y equals 0, the x-axis. Okay, so the degree, let's look at this example right here on the side, 2 over x plus 1. The degree of the polynomial on top, the constant 2, has the degree of x to the power of 0. So that has a degree of 0. The denominator has a degree 1. So the top's degree is less than the bottom's degree. So it's bottom heavy. Bottom heavy rational functions have a horizontal asymptote on the x-axis. Part B says if the numerator and denominator have the same degree and the function is in the form where you have the lead coefficients and everything's in the order of, each term is in the order of their powers from least to greatest, the two lead coefficients will be used as the ratio which will represent the constant for the horizontal asymptote. So it'll be at y equals, notice the coefficients over one another. So that's at the same degree. C, if the numerator is exactly 1 degree more than the denominator, then we'll have an oblique or slanted asymptote. Right? So a slanted asymptote happens when you have a top-heavy rational fraction, but it also has to be exactly 1 value higher. And to find it, we divide the numerator by the denominator and disregard the remainder. Set the rest of the quotient equal to y to obtain the equation of the asymptote. So example 4 here, let me zoom out a little bit. For each rational function f, find all asymptotes. So part A has a degree 1 in the top, and then if you were to FOIL this out, you would have 2x squared as the lead coefficient. So this is bottom heavy, so this will have a horizontal asymptote at y equals 0. Part B, they have the same degree, so the horizontal asymptote will be at 2 over 1, because the lead coefficient of the top is 2, the lead coefficient of the bottom is 1, so 2 divided by 1 is 2. So at y equals 2, there will be a horizontal asymptote. For part C, it's top heavy by 1 degree more, because this is degree 1 in the bottom, degree 2 in the top. There's a difference in their degrees of 1. So what we would have to do to figure out the horizontal asymptote is divide the top, divide it by the bottom, and disregard the remainder. Which we'll do, I'll just show you what they have here already. I might have to turn the page to get to it. Let's see. Okay, so you can see here, the division is being performed, and the remainder ends up being 5 over x minus 2, which we disregard, and the leftover is the horizontal asymptote. So there will be a horizontal, an oblique, I meant to say, an oblique asymptote. Am I saying that right? Yes, an oblique asymptote at x plus 2. So that would be the slanted line going through the y-axis at 2 with a slope of 1, a positive slope of 1. Let's back up to also look at what the vertical asymptote should be. A, the vertical asymptotes will be wherever the denominator would equal 0. So there should be a vertical asymptote at x equals positive 1/2 for this factor, and another vertical asymptote at x equals -3. For part B, there will be a vertical asymptote at x equals +3, and for part C, there would be a vertical asymptote at x equals positive 2. Okay, so you can see that here, x equals 1/2, x equals negative 3. For part B, get down here. Oops, where'd it go? This thing's very slow and finicky. Let me see. Can I? Oh, no, no. Maybe it's my mouse malfunctioning. Let's see. Try it again. Okay, yeah. So here's your horizontal asymptote at 2. Now they showed it out doing the division, which explains why this is a fact that actually holds true. If you do the division, you end up with 2/1 when you disregard the remainder. So then setting the denominator x minus 2 equal to 0 shows the vertical asymptote at the equation x equals 2. And so let's go on, see if there's anything else I want to show you in the book, and then I'm going to switch over to doing examples in a new video. Okay, so the summary here is to find any vertical asymptotes, then any horizontal or oblique asymptotes, then find the y-intercept and the x-intercepts. That will give you a good starting point for graphing it. Then you go on to determine whether the graph will intersect its non-vertical asymptote by solving f of x equals b or f of x equals mx plus b. Okay, so what that means is that for the horizontal asymptote, sometimes they do cross. Sometimes the function will cross a horizontal. It will never cross a vertical. So you can rely on the fact that your vertical asymptote will be like a wall or an electric fence. However, for the horizontal and the oblique asymptotes, sometimes they'll cross and sometimes the function will not cross. And so we do have to see if there's any point that the horizontal asymptote shares with the original function by setting them equal and then solving for x. So I'll show an example of that when I start doing the example videos. Then you want to plot selected points in between the asymptotes and intercepts to get an idea of the behavior that's happening in between those values and to complete the sketch. And notice it's called a sketch because at this level in algebra, we're not expecting you to come up with a perfectly accurate picture. But if you have considered all these points, taken all these steps, you'll have a pretty good reliable sketch. All right, so I'm going to go ahead and switch over to working out examples on my tablet. So if you have any further questions regarding anything I've discussed here, it might be worth it to you to go through the textbook a little bit. There are embedded links in some of these pages to like videos or applets, which can be helpful. Also, I want to remind you that there are videos that the author has provided to go with the textbook, which can be great as well. But I'm going to start doing examples much like they're shown here. Like this, these are already examples done for you, but I'm going to do some from my own perspective. But these are also really well done. And another great resource. Let me see if I can open one in a timely manner. Right, so they're going to go through all the steps of understanding the behavior, finding the asymptotes and the intercepts, and then inspecting or investigating what the behavior is between those values. Right, so I'll see you on the other side in my next video, and I'll stop talking now. Bye.